All right, guys. So just for you to be able to see the whole picture um, about the potential and the potential energy, the potential itself, the electric field and electric force and everything. But I mean, most of the stuff that we actually trying to deal with are the field and the potential. So I have a website that once again give you some simulation, and I think it's much better than my drawing. I'm pretty sure it's gonna look way better. Okay, give me a second here. I got a link for you guys. I think I had too many windows up here. Okay, it's right. I found I found new one that actually looks really good. It's actually I haven't seen this before I like started like do the search again. So I'll send you the link that actually jump directly to that. Here we go, guys. Okay. There you go. All right. So you guys can sort of like click that link, and there is a simulation that you should be able to take a look at. So I will do that. Let me share another screen here. There you go. I don't know, is this the right one to share here? There you go. Okay. There, already. Okay, so I think this is good. Can I pop this one up? There you go. Okay, all right, guys. So this is what you have. And the good thing about this one is actually you can play around with it, even though I don't really understand much about the interface here. But what you can do is you can pick between the positive and negative, or you can see both positive. So it's sort of like there is like a preset, or you can have like an arrays of positive and negatively charged. See, it's kind of nice. And you have a button that you can push here to display or not display the electric field. And there's a button that you can play to display the potential or not. And as you can see, okay, let me switch back to just point charges here. So as you can see, the field, okay, so we kind of got it, that the electric field point diverges out from the positive charge down to the negatively charged. All right, and they do a better job at actually drawing the size of the arrow. As you can see that the bigger the arrow means the stronger the field. So that's kind of nice. Okay, so what you can do is you can actually, I think you push that button and then you can drag this sort of like there's a crosshair over here that you can move around just to investigate the size of the electric field. As you can see, if you get very close to the field, this electric field is strong. And when you go further away, electric field is weaker, but it's pointing towards the negatively charged particle. And then when you get closer to the negatively charged, the electric field will point towards it. Yeah, cool. All right. Plus, what else you can do is once you click on it, it will draw electric field lines. So what it does is just connecting all those tiny, tiny vectors, arrows, and we understood that the directions of each vector of the electric field vector is going to point tangential to the electric field line. So that's why every time you click on it, it will draw electric field lines at the position of that crosshair there. Is that cool? All right. Not only that, at this situation over here, they use the color. So we're trying to use the red color for the hot, and the blue is for the cool one. So it means if you think in terms of the elevation, so it means like the potential around the positive charge, which is the red one, is kind of like high. So that's sort of like you are at the top of the mountain. And then when you go to the blue, it's like you're going downhill, and then you go actually deeper underneath the ground level. So you have like some sort of like an abyss or something like that. You dive down into something like a big hole there on the left. However, if you press the button on the V, that will give you on and off to display the potential strength, right, or the height, right, the elevation. But the good thing about this one is, can I clear this whole thing? Okay, what you can do is I can just get rid of all that. And now what I'm gonna do is, I'm not so sure about the interface here, but that's what you can do is now I am turn on that violet or purple ring over there. And then when you press the crosshair there, it will draw and something that we call is a constant potential line. It's an equipotential line. So see, so now I start to build that contour map that we studied last time. Isn't that cool? All right. And as you can see, there is a label on it. So when you are closer to the positive charge, that label is positive because you are higher. Yeah, you are up higher. And then when you move out, that's lower number 18.9, 10.7 plus 9.5.9 on and on until you are somewhere in between. I think that is going to get very close to zero. Can you see that? Okay. And that's where you're going to face the zero potential because of the cancellation between this negative and positively charged. And then we go to the left hand side. Now you're going downhill even further. All right. So you get down deep into like a hole or something. There is a hole there. And it's sort of like now once I draw these lines, then it seems like it looks like a contour map. And I think you have a better picture of what it means by when I have like rolling from the higher elevation to a lower elevation. So that means if you have a positive charge starting from the right side of this diagram over here, let it go. It will just gonna roll to that negative side there. Yeah, from high to low. But if you have a negatively charged, think of it like an electron, you have to let go from the negative one and it will just roll uphill, to try to get up to the positive charge. Isn't that cool? All right. So I think this is a good it's a good sort of like a simulation that allow you to understand the relationship between the field and the potential. And as you can see, at any single point, you see that the electric field potential, okay, I'm sorry, field potential, what's that? Electric field lines cut the constant potential line or equipotential line in a perpendicular fashion all the time. See that? Every time that these two lines cross, the purple one is the constant potential lines, the contour map, the contour line of us, and the black line, that was the electric field lines. They always cut in the perpendicular fashion all the time. Okay, so that's the relationship between these two. Okay, cool. Nice. Already. Okay, so I think you guys can play around with this for a fraction of minutes. I'll just go grab a drink. That's all. Give me a second. All right, guys, play around with this. Oh, okay. Someone send me. Okay, okay. Got my email. I'll check it. Okay, guys. All right, guys. So I think that is good, and I hope this will summarize uh, what we were talking about: electric field, electric potential, and everything. Let's switch back mix up that last exercise that we had in our class. Okay, all right. So the only operation that we need, right, even though now we understood it graphically, that the electric field line always touch the equipotential line of the contour map, the contour line of the potential in a perpendicular fashion. The relationship between the two is just going through this operation right here. As I told you last time, even though you don't understand the underlying sort of like the foundation of this vector calculus is in full detail, but the operation is just like a recipe that's very easy to follow. Yeah.
Okay.
So in the sense that all you need to do is just take the potential function derivative, do the differentiation with respect to x. You wait a second. You haven't heard. Okay, so did I just turn off the mic? But at the time of the simulation, you heard me, right? Oh, it started. Okay. All right, sorry. Oh, that's my. I think it's now my normal reaction. Every time I move away, I have to turn off my mic. Okay, thank you, guys. Sorry about that. Okay, so I hope that you have seen the graphical interpretation, the relationship between the fields and the equipotential line, or you can think of it like a contour line from the potential that they are always perpendicular to each other. The operation that links these two quantities, the field and the potential, is very easily connected through this operation here, which is every time that you are given the potential function v, take the derivative with respect to coordinates. Yeah, and in this case, you are doing the Cartesian coordinates x, y, and z. So you just take the v, differentiate with respect to x because you only care about the x. So you're doing the partial derivative. Does that make sense? All right. Okay. So whatever you do with respect to whatever coordinates you're talking about, you're going to get the electric field pointing along that coordinate. So if you take derivative with respect to x, you get the x component of the E. And don't forget to slap the negative sign into it because the agreement of us was electric field pointing downward. So it's point from high V to low V. So that's why there is a negative sign there. That's it, guys.
Okay.
So last problems I just want to wrap up this thing is just given right here. Okay. So the electric potential at points in XY plane is given by this. So this is good. It's only two variable function. So that means everything is already on an XY plane. That's kind of nice. All right. It's not even like a three variables function. In units vector notation, so that's mean that was the IJK. Yeah, that's the unit vector notation. Yeah. What is the electric field at a given point? 3 and 2. All right, guys. You want to give it a shot here? Yeah. So for this one is, well, just go ahead. We only have one recipe to follow, which is just the derivative with respect to the coordinates. So over here, let's do it, guys. If you want electric field along the x-axis, so that's your x components of the electric field, you take the potential, differentiate with respect to x alone, so that's a partial derivative of v with respect to x, and don't forget to slap in the negative sign there. There you go. All right. And then you do derivative of this one. I mean, this one looks a little bit dirty. It's just because there is a unit right in that numbers there too. So that's why it looks a little bit like, you know, crazy looking, but actually overall, it looks just like this. If you treat everything as an SI system, so that will look just like 2x squared minus 3y squared. So the derivative with respect to x will give you 4x. All right. I'll just minus 0 for you just to make things clear here. Cool. And that is negative 4x. That's the x component of the electric field. The y component, same thing, negative dv by dy. Negative is first one. The first derivative gives you 0 because x is just a number. And now you get the negative 6y from the second term, and that is positive 6y. So if you want the electric field in the vector notation in general, you haven't specified any particular location on an xy plane. You just say electric field vector is going to be just exi plus EYJ. Or that is just negative 4xi plus 6yj, guys. That's it. It's done.
Okay.
Okay. Plus, if you want the electric field at 32, where everything, the units are all in SI system. So all you need to do is just plug in the number. All right. You see X anywhere, you just substitute it with number 3. So that's negative 12i plus 12j. Isn't that cool? All right. And from here, if you want to find out what I want the magnitude of this electric field at this point, you just do the negative 12 square plus 12 square. So it's just a 12 root 2. So that will be the strength or the magnitude or the value of the electric field at that point. And you know the direction that it's pointing to. Yeah, cool. And that is it, guys. Done.
Okay.
So I hope by following this sort of like straightforward recipe here, that's it. That's all you have to worry about. Just doing the derivative with respect to the coordinate system, slap in the negative sign, and you are done, pretty much. Any questions so far? All right. So if I think this is the guarantee. I think there must be one question in the final exam here, and this is guarantee that you guys will be able to grab this for sure. All right. Everyone should be able to do this 100%. Nice. Okay, guys. So that is it for the topics about the electric field and eventually electric potential. And now we have the relationship between them. So I'm going to pull up the next handouts. All right. Because you guys are having the exam this Saturday, and I don't want to sort of like give you so much stuff at this point. So I think I'm going to try to run this lecture a little bit brief, and I'm just going to introduce just one concept today. Sounds like a good plan? All right. So we might be able to just end today's lecture a little bit earlier, and I don't want to have to talk too much about the concepts that is over here. So what I'm going to show you today is about the electric flux. Okay. And I would say you are about to get to the highest point of the course. I will consider this one to be the hardest or the most difficult part of the course. It's the Gauss's law. All right. And even though I said the hardest one is not because of the mathematical complexity or anything, but it turns out it's underlying inside the way that you need to do the calculation using the concepts of flux. That's it. That's a problem. So that's why I just want to spend a lot of time talking about flux, because once you understand what the flux is, Gauss's law is just, well, it seems like they just utilize that concept and just, I don't know, it's just like a straightforward plug and play. So it's just like, if you know what is flux and you just apply flux to electronic charges and you just slap the name on, it's called Gauss's law.
Okay.
So that's why, to me, the crucial part of understanding these topics about Gauss's law turns out to be understanding how to calculate flux, guys. That's it. Okay. And once you have that, we slap in the Gauss's law, we have the name for it. And now we can actually move on to the application about the capacitor and what does it mean by the capacitance. And that will be just later next week. Sounds like a good plan? All right. So just going easy, guys, today. Don't want to put too much stuff in your head right before the exam. So what is electric flux? And I think if I have enough introduction about this topic and have something sort of like running in your head, I think I'm just going to leave it there today. Okay. And just finish the second exam first, and then we can continue on later. Okay. So what does it mean by flux? So we have already had the electric field lines, right? Okay, we had the lines. And the good thing about that lines was just like, okay, you have the information of the field and the potential per se. I mean, if you cut those lines perpendicularly, you get the equipotential surface or equipotential lines that come in the form of the contour. Yeah. However, if we move back to the lines one more time. So we would like to take sort of like the field line to be at our center stage one more time and put the spotlight into it. And just want to learn a little bit more about what does it tells you, those lines. Even though just single lines will tell you the direction of the electric field, right? But a bunch of lines will give you something else as well. So I think you remember the one that we talked about. If you look at this one, you say, okay, Ajahn, if you have a bunch of lines here and you somehow you draw an area, so this line will just piercing through, sort of like they're just crossing those area A. And everyone seems to agree from last time. Okay, I can draw you like we had a figure something that looks something like this. If you remember vaguely, there is an electric field line that actually spreading out. And I was asking about, hey guys, if I have a surface area over here and have the same size of the area at two locations, let me call it location number 1 and location number 2. You guys can tell right away that the electric field strength, the strength of the field at the location number 1 is going to be higher than at the location number 2. Does that make sense? Right? So everyone can solidly agree with me that the electric field at point number 1 is stronger than at the location number 2 because the line's density is higher at location number 1. Cool.
Okay.
That one you guys agree. Okay. So what you had there, I was just saying that there must be some connections about the density of lines. And when I say density of lines, you are looking at the density across a surface. And here we go. Introducing the surface area right here.
Okay.
So what you are trying to look at is how many lines that actually going through one particular surface. And if you can make that connections, I mean, just take the ratio to represent a density. So you want the number of the lines per unit area. You can call that the line density, right? It's a density per unit area. But that will eventually lead you to the magnitude of the field. The denser the lines per unit area, the higher the field. So that's why I put the proportion symbol over there, just saying that, okay, they are proportionate. And just to make things nice, the number of field lines, that we're going to call it flux, guys. That's what it is.
Okay.
Flux. Like the lines, something that's whatever going through space. So, and we use the notation of the capital phi in Greek letter here. That's flux right there. So I can turn this into an equation and say it's going to be about, okay, because they're going to relate it somehow, don't introduce any constant into this relationship and just take the flux per unit area and call it good. All right, this one is just a matter of definition here. So that means you can move things around and say you can figure out the amount of flux, which is now is just a number of electric field lines, to be just a product between the electric field and the cross-sectional area. You have to pay attention to the word cross-sectional area. Because if you want to count all these lines supposed to go through the area in the perpendicular fashion that you want to take into account. Otherwise, then I'm not going to call it good. For example, if there is another line that going in this direction here, just glance through but not penetrating the area, you're not going to call that electric flux that going through your surface. Does that make sense? Because there's nothing going through. It's not passing your area. It's just passing you, just lying around there, but never going to cross the boundary of your area there. So this one, you're not going to call it electric flux that going through your surface area. Does that make sense? All right. So you want to just take into account the lines that actually going through the surface in the perpendicular fashion. Otherwise, then you will have another problem. If I have the flux that somehow go in some angle, whoa. Yeah. It's not piercing through perpendicularly. How will we deal with this? Easy. We can break it into two components. You can do horizontal component and perpendicular component. You guys with me here? And you only going to take into account this one, and you throw away this component there. So that's give you a sense of what we are about to do here. So when you have a flux going through a surface area, the only thing that you're going to count as the lines going through that area, you're going to have to count it only the lines that piercing through perpendicularly. So that's why I have a perp sign over here. It's a perpendicular. So you can only think of this one just like, okay, I'm going to take the electric field, multiply by the surface area that points, and that's not point yet, just the surface area that's actually line oriented or sort of like, you know, have the orientation perpendicular to the electric field. Cool? All right. The one that is going to be parallel to the field lines will not be taken into account. Nice. Okay.
Okay.
All right. So far, so good. So that's why your formula looks something like this. It's a E times A, but that A has a special orientation. It has to be the perpendicular orientation. Okay. It's still not done yet, right? It's still unclear about that. Okay, I got the concepts a little bit. So let's look at some comparison, shall we? So look at these two scenario, guys. So on the right and on the left. On the right, that looks kind of nice. That's what we want. We want the electric field that piercing through the surface area in a perpendicular fashion. We want that. But in reality, it might go something like this. You have an electric field that looks very uniform and nice, pointing downward, but then the area that you are interested in is not lying perpendicular to that electric field lines. And it's, let's say it makes some angle over here. So just to make it a little bit clearer, let me draw the side view of this one. So the side view of this, it will go something like this. Yeah, does that make sense? All right, so this is a side view of the scenario that you're looking at over here. There you go. That's a side view. So electric field pointing down, but your area is actually making some angle with it. In this case, it's given to be theta. How will you deal with this flux calculation, guys? I want to know the amount of flux going through this blue area here. Do you think how much would it be? But it's not that bad because you already just told me that electric field is actually pointing downward, right? So what you need to do is just break this into two components. See? Okay. And once you're done with that, you take away the original. Okay, that's fine. All right. And this is the one that you don't care because that parallel component is not piercing through your blue area here. You only take into account the one that actually going through in a perpendicular fashion. So if this is the E, you're doing the theta calculation there. Theta is given there. So the angle theta is supposed to be this theta right here. So the component that you will take into account is going to be just the E cosine theta. The E sine theta over here, you will throw away. But Ajahn, I'm not going to do this. That's not counted. That will not be counted as a flux through the surface. The only amount of flux that the only flux that going through is just only E cosine theta components. And then I take this E cosine theta, multiply with the surface area that's given there. That is my flux. So that's why it's down here. Cool.
Okay.
You get the idea here. How you do it. Okay. So you only want to take care about of the electric field that has a direction perpendicular to the area. That's all you need. That's all I care about. Okay. But now here comes the trick. This trick goes a very long way back in your history of physics. All right. You remember, is there anything that you need to do something like this before with this kind of formula? Does it look familiar to you? So like E times A cosine theta. There was like, there was something there. Remember the work done again? The work done was just F times S cosine theta. That looks very familiar, yeah? Done, yeah, because you had cosine theta there, so that might be. But the force itself was the vector before. So you put just the magnitude of the force here. The S that you're seeing over here is just a displacement. And then you just say, hey, I just want a cosine theta. So that means you just take the displacement that is pointing in the same direction as the force. But the point is, I can also equally write this equation like this. Nobody will have any problem with this. And what you saw before was just like, okay, and actually this is what you mostly do. You take the force, break them into two components, and then you only take the components that actually point in the same direction as the S. I think that's more practical that way. So if I draw like a scenario for you here, if you remember this, I have a force here, make some angle theta, and drag this mass with the distance S. What you did was just you break the F into F cosine and F sine theta. And you said, but that F sine theta doesn't do any good. It doesn't create any work done. That's why you only take the F cosine theta, multiply by the displacement, and hence you get this relationship. You get this product here, F cosine theta multiplied by S. That's your work done, right? Okay, but now zoom in here. What about the first equation over here, guys? I can put parentheses here. So actually, I can do the same thing with this. Instead of breaking the force into two components, I can do the breaking or decompose the displacement vector. Nobody will have any problem with me. I have the S over here. That's my S vector. I can break the S that point along this and perpendicular. Same thing. I keep F, the force, untouched. I only break the S. And what you get here is that this is S cosine theta. See? And this is S sine theta. I once again throw away these components because the S sine theta is perpendicular to the force. That's not our definition of work done. The work done is just the force multiplied by the displacement in the direction of force. See? This even sync with the description better. Because when you talk about this one, what is the definition of work? Is the force times the displacement in the direction of force. But when you do it, most of the time, you do the F cosine theta. You do the force in the direction of the displacement. I don't know, I'm confusing you or not, but they are equivalent. That's what I'm saying. I'm trying to say is you can decompose the F, take only the one that is actually pointing along the displacement, that is F cosine theta. Or you can do in the other way around. Just say, okay, John, don't touch the F. The force is there. I'm just going to touch the displacement S. I'm just going to take the S cosine theta and multiply by the F. I end up with the same thing. So that's why I rearrange this into two forms over here, just to showcase that these two products are exactly the same. It depends on your approach. You want to break the S vector or you want to break the force vector. So when I say this, now I want to do the same thing with what we are doing over here. Can we do that? I know I'm talking too much today already. What I'm going to do today is I'm going to do the same thing. Well, John, that cosine theta actually can be paired with the E and leave the A alone. And actually, what you are looking at over here, this is what we just did. See this? And this? See? I actually just take the E components, the components of the electric field that is perpendicular to the area A, and do that product. So that means I can do the same thing. I can pair the cosine theta with the A instead. See this? And that's what I'm about to show you. That you can do two ways. Instead of breaking the E, I am now going to define the area vector, guys.
Okay.
The area vector is a vector. It's not just width times height anymore. This is the weird one. This is the weirdest concept in the sense that every time we talk about area, I think you guys think of it like it's a scalar quantity, right? The width times the height. But in reality, you think about it carefully. When you have a piece of paper, okay, let me grab, I don't know, it's something that's kind of obvious here. Okay, I have a piece of paper over here. All right, you can figure out the width, the length, that's no problem. You know the area over here, everything is good. But then the point is, there is orientation of this paper. You see that? Right? So actually, with that orientation of this, you can turn this paper into a vector with the area on it. So you know the area, cross-sectional area of this paper, but you want to attach the information about the directions as well. So you know which orientation of this one's supposed to be in space. Yeah. So it's very reasonable that you should be able to assign a vector properties onto a surface area. And that's what we're going to do here. So what I'm going to draw is this, guys. If you have a piece of area here, and you know the size of this one is A, the definition of the area vector is very easy. You draw a vector that is pointing perpendicular to that actual area, guys.
Okay.
That's our agreement. That's what we're going to do. Okay, so whenever you have an area, the vector of that area is going to point perpendicular to it. So you put arrowhead on top. So you guys with me now? Okay, so think of it like every time from now on, if you have a cross-sectional area at any place, you can just draw an arrow sticking perpendicular to that actual area. You will get the area vector automatically. Come back here, over here. Yeah, I can draw this. That's my area vector. Since, yeah, makes sense? But there's one more problem left. Bajan, you have two sides. Why don't you draw that A backward? There are two sides of a paper. Which direction you want to pick? You want to go this direction or that direction? Don't worry, because in the theory to come, the surface eventually will be a closed surface. When I say closed surface, think of a balloon. So if you have a balloon, surface is closed. We will define the outward direction to be your area vector. That's your area vector. It's coming out. So to me, the easiest way to think of the area vector is your hairs, hairs on your body. So think of it like if you see a ghost or something and then your hair just like stand up. Yeah. So the direction of the hairs, that would be your area vector of your skin surface. Does that make sense?
Okay.
Okay. So assume that your hair is supposed to be sticking out as well, right? I mean, my hair on the top. And but I mean, if you have like your hairs on your hands and everything, the one that's sticking up, those are area vector pointing out. And you assume that your body is a closed surface. Okay, cool. All right. So with that in mind, so over here, come back to our scenario over that you'll see on the left. You can draw an area vector if you like. Going that direction. That's your area vector. All right. This one, I just picked the one that actually go along with the electric field that's pointing down. I mean, because right now this is an open area. So you might just say, but John, I can define it the opposite direction as well. So that's no problem. But for now, let's assume that it's pointing down. Just to display the point of breaking this into two components. That's all. I just have to break this one here into two components there. You guys with me? Okay. And with that, you can just throw away the horizontal one. You only keep the vertical one. This is the one that you keep, just the vertical one. But then think backward, guys. When you only have just an arrow of the area vector pointing down, what is actually the real surface that this area vector is supposed to be representing? You guys following my logic here? You only think about this downward vector, right? This is the area vector. This is your vector components, right? This is A perpendicular vector, yeah? But what does it actually representing the real area? The real area is supposed to be always perpendicular to the area vector at all time, right? Does that make sense? Okay. So that's what I'm saying over here is when you have the A perpendicular components here pointing down, it must be representing the actual surface that is horizontal. Let me write it on the right here, guys. I hope this gives you some connections here. Does that make sense? So the figure on the right showcase what I am trying to explain to you. I am having the area that is make some angle with the electric field. Instead of doing the electric field decomposition, instead of breaking the electric field into two components, I choose to break the area vector instead. And by doing that, I will only take the one that is perpendicular to the field. So the actual area that is perpendicular to the field is on the right side figure here. However, from the definition of the area vector, the vector itself actually is going to point perpendicular to that blue area there. So that's your vector is pointing down. And that means what you really want is the E vector and the area vector, they must be parallel to each other.
Okay.
Does that make sense? Yeah. Okay. So that's what it is. So in reality, what do you want in terms of calculating the amount of electric field lines going through the area? You have to do it in the sense that E, the electric field vectors, going through the surface in a perpendicular fashion. Okay, so this is how I'm trying to wrap up things here. But because we define the area vector to be perpendicular to that area, so what you really want is just the E vector that is parallel to the A vector. By having these two parallel to each other, you are guaranteed the condition of the E vector is actually perpendicular to that area. And that's my conclusion.
Okay.
Is that confusing? All right, I would say this is going to be the concepts that takes a little bit of time to digest. But I hope by subtle, I don't know, I spent like the whole lecture just talking about the definition of flux and how to calculate them. You will have a clearer understanding of what does the flux is trying to represent, what is the A vector is trying to represent. And once you understand the A vector and what does it mean by the flux that we want, now we understand that we can get the flux by taking the E vector and the A vector that they are pointing in the same direction. Having the E and the A pointing in the same direction is guaranteeing that the E vector piercing through that area A in a perpendicular manner, just like we want. Cool. I hope that gives you enough conclusion over here. And once you say, hey, Ajahn, I just want two vectors that actually parallel to each other, that's why now I can come back and compare these two lines of equations one more time. Once you define the vector A, you only care about the E and the A that are parallel to each other. Remember, we used to write F as the F dot S. Yeah. Now, can you guess what should be the equation for the flux? Yeah. Very good.
Okay.
Is the E dot A. Flux can be calculated by taking the electric field vector, do the dot product with the area vector. So that's why it's so crucial that you understand how you define your area vector. you define it to be perpendicular to the actual area. So you want the flux to represent the electric field lines that piercing through the area in a perpendicular manner. That's exactly what we want. That's the electric field vector to be parallel to the area vector. That is what we want. And we are done.
Okay.
Cool. So I don't know if this is like very confusing or not, but I think this is a good place to take a break. And after coming back, then we'll dive a little bit deeper on how actually we can really do this thing. So for those of you that come back a little bit earlier, early, then you can take a look at this slide, and that will give you the same conclusion that I just made previously. Okay. All right, guys, take a little break right here, and then we'll continue on later after the break. Okay, so this slide just summarized what I just told you about. That from now on, if you would like to speak in terms of the area vector, all right, and the electric field vector, so this is what it is. You're starting from this, you have some area A, and now we understand that you can assign your electric field, the area vector perpendicular to it. They call it a vector. Cool? All right, now, with that assignment of the electric field and the area vector in this way, there are two ways that you can think about it. Is you can break E into E perpendicular, see? So you just bring in just the component of the electric field that actually perpendicular to the area. Or on the other hand, you can go backward. You can just break the E or the A vector that actually point in the same direction as the E. That's it, guys. You are done.
Okay.
I hope this clear things up. Okay. These two will eventually get you back to the same conclusion of the flux, because now the flux means it's just either E pointing in the same direction as the A, or the A is pointing in the same direction as the E. So it's just the E dot A. And if you guys remember, the property of the dot product is the same as the A dot E. And because this A dot E or E dot A, the reason that they are the same because it just has the value of the EA cosine theta. And just like the previous slide, it's equivalent to writing as the E cosine theta A. It doesn't matter. Cool, guys? So this is nice. All right. So to be properly assigned the area vector into it, and just for the future benefit, what you can think about the area vector, you can write it out in this form over here. So whenever you have an area vector, it's, of course, vectors always have the magnitude and directions. So the magnitude is definitely just the size of that area, just like what I just told you. Yeah, the one that you said that, hey, if I have just a paper, is the width and the height, that is your surface area A there. But now you want to assign the direction to this, you just multiply by the n hat. The n is just for saying that it's normal. Normal is perpendicular. So that's it. That's how you define the area vector. It's just taking the normal direction from that actual surface. That's n hat right there. And you are done.
Okay.
Cool. All right. So that's give you a very nice conclusion of how you define your area vector. And once you get that one down, that's the definition of the flux of an electric field through that area. Cool? Nice. Very cool. All right, yeah. And this is the consequence of that. So now think about it. In reality, as I told you, eventually we're going to take a look at the surface that actually wrapping itself around in a closed form. So you have a closed surface, like a balloon over here. See? Now, imagine this along with me, guys. If I have an electric field piercing through this balloon, all right, just like that, okay?
Okay.
And I'm just asking you, but hey, guys, take a look at the point number 1 on this balloon. So we have some sort of like a, have an area over there. And then, hey, give me the electric flux through this area number 1 here. What would you do? Well, that's easy. First thing first, You just have to write the area vector of that piece. All right, let me call this, because this could be like a tiny area, so you can call it a delta A. And you guys sort of know in your head that delta will turn into like a differential very soon, right? Okay, but anyway, for now, let's just a mini portion of the area. And at this location, the electric field is going to point along that electric field lines there. So as you can see, if you want to find the net flux on this one, it's going to be mini one as well. Let me call it like a delta flux here. It's going to be just the E dot with that delta A vector. And this is just the N hat. You guys with me here? Okay. N hats just signify that the vector is perpendicular to the surface. And that's it. It's going to be E delta A. And then all you need to figure out is, Ajahn, what is the angle over here? Theta, cosine theta. That's it. However, you can see from here that the theta is less than 90 degrees. Cosine of something less than 90 degrees, you still have a positive one. So you have a positive flux over here on the surface, number one. Does that make sense? All right, of course. Then you have an opposite case. If you sort of focus on the surface number three, shall we? Which is sort of like toward the back a little bit here. Okay. So over here, Ajahn, that's no big deal. I can draw the area vector over here, mini area vector here again. Okay. But electric field at this point is going to point in the same direction as usual. The E will just point from left to right. Now you start seeing that, hey, Ajahn, now your angle is kind of huge. The flux on this one, let me call it a mini flux again, is still same equation. Nothing has changed. It's just E times A with the dot product there. So it's still E delta A cosine theta, except now your theta right now is big, larger than 90 degrees. So in this theta over here, let me highlight green over here. This one is going to have the value less than one less, smaller than one. So that means, I'm sorry, smaller than one, definitely. Small is negative, smaller than zero. Sorry, my bad. It's going to have the value less than zero because it's already go beyond 90 degrees. So that means the flux number three over here, you're going to give a negative flux. Cool. And of course, that will be a case that make you coming from the positive ends to the negative ends of this one. And that will be the case of the area number two there. And that is just like, oh, the area vector over there is just a perfect 90 degree with the electric field at that point. And we already agree with this one, Ajahn. When the E and the A are perpendicular to each other, that means the actual area doesn't get penetrated by the electric field. No, it's not. So in this case, of course, because the angle between them is 90 degrees. So when they are 90 degrees, then of course the flux here is going to be zero. See? So this is a conclusion that from the definition of the flux that we just introduced here, you can have positive flux, negative flux, or no flux. No flux is easy because it's just come from the case that there's no penetration of the vector through that area. That's all. Cool. All right. So that's what it is. But what can you start to get the feeling of what flux really means now? Can you tell me a little bit here? From this figure over here, can you sort of like start to make some connections what the flux is? Now you can think of the flux as, okay, it may be something more natural to you if you think in terms of like a stream of something, like water stream, or it could be like a heat stream. There is like a heat flow, and you sort of like represent that flow with the arrow. Yeah, think of it that way. And there's so many ways that you can think of this one. You can think of this like a stream of some movement of something, water's flow, heat flow, the what kind of other flow that you get, like maybe air flow or whatever. And then what you are seeing over here is when flux is positive, it means like the flow or that stream or that arrows are coming out, try to escape or try to run out from the enclosed volume. See this? Yeah, this is out. Something tried to come out. On the other hand, when you move on to the other side, when you have a negative flux, it means something is trying to get inside that volume. And when you have a nothing, when you have zero flux, meaning it's just not doing anything, it's just piercing by. So it's not entering, it's not exiting, it's doing nothing. So the concepts of flux now start to understandable to be in terms of like it's telling you the change of that stream or whatever the things that you represented as those arrows. That is like is coming out or is trying to entering. It's kind of like going into. Does that make sense? Okay, so with that idea, it seems like flux will be able to tell you what is happening inside this closed volume. Over here, if you say, well, Ajahn, well, if in is equal to out, so it means whatever the coming out of this is equal to the one that's coming in. So you can say the net flux within this closed surface is 0. So this means there's not going to be any leftover inside this balloon because out is equal to in. So that means you can tell whatever the electric field that actually piercing inward will be canceled out with everything that's piercing outward. So there's nothing left over inside this enclosed surface or enclosed volume. Does that make sense? Isn't that cool?
Okay.
All right. That's the sense of it. So that means we are going to really focus on a closed surface only. The reason for that is because we're going to actually deal with something that's wrapping something around. We're not going to have like an open surface in our discussion whatsoever. Cool. So that means now I can turn the calculus on a little bit now. And that tiny area that we call it, we can call it like a mini, super duper small area. And we can say that is the infinitesimally small surface area, dA. So the flux that going through this is going to be super duper small as well. So you can call this like a mini flux there. So the mini flux is just going to be E vector dot with the dA vector. So that you can turn this into a vector there. Cool. And now you just keep doing this everywhere on this closed surface. You just keep doing to the next one, next one, next one, next one, next one, next one, on and on. So what you're doing is you just sum all those flux together. At the end, you will get the net flux through this closed surface. And that's how you calculate the net flux over any closed surface. But because your surface is always closed in our discussion, that's why we emphasize by putting a circle symbol on top of the integral sign, just to saying that this integral is going to be over the surface, but it's closed surface. Cool? Alrighty, very nice. That's
Okay.
what we're about to do here. See, over here, can you see something here? If you see electric field line piercing out and your closed surface look like this. So what do you think about the net flux of this one? Positive, 0, or negative? Yeah, it's supposed to be positive, right? Because on the surface of this one, the area vector, which I do it in like a differential form over here, and the electric field is coming out. See, they are pointing in the same direction. So cosine 0 is always positive here. So the net flux is supposed to be positive on the first figure. Sounds good? Try the second one here. What about this one? What do you think about the net flux on this? Bỏ Ajahn, yeah. There is top surface, there's bottom surface, and there are side surface here, right? The side surface doesn't do anything because electric field doesn't seem to go through the side surface. You only have to worry about the top and the bottom surface over here. But from the look of it, Ajahn, it's coming in from the top, But whatever in is actually goes out. So it's like in equal to out. So you should be able to sort of like guess that the net flux on this one is supposed to be 0. Does that make sense?
Okay.
Yeah, in equal to out. So there's no leftover in there. Same thing on the right. Over here, well, okay, done. From the side, that's nothing there. The only thing that seems to be able to give you something that's non-zero is going to be on the left surface here and on the right side surface there. But once again, whatever in from the left seems to goes out equally. So it looks like the net flux on this case also 0. Cool?
Okay.
All right, so that's what we're trying to say about, okay, first sort of like skill that we need to build is how can we calculate the net flux across any closed surface? Okay, and once we have that one skill down, then the rest is going to be pretty simple. And the connection to the Gauss's law will be super, super obvious. Okay, all right. But actually, I can like a spoiler alert here. What do you think these 3 cases have something in common or something different? What do you think? The one on the left have the net positive flux. The other 2 doesn't have anything. Can you start guessing what is this supposed to sort of like? Anything that comes into your mind at all? Anything? Very good. Whatever you're thinking is correct. I don't know what you're thinking for sure, but I'm sure that you're thinking of something. On the left one, it looks like the net flux is positive. It's like something is coming out. This is the case that you have a positive charge in the center, right? At the center, if you have a positive charge, then you will get an electric field coming out of it, coming out of it, coming out of it. So that's why it's give you a hint of if you have net positive flux, there must be something inside that generate that positive flux that coming out. So it's like something that's, something that just, generate this flux out. But in contrast to the other 2, can you see? It's in equal to out. When you say in equal to out, that means that electric field must be generated somewhere else. And it's just like passing by and then just go through. So there shouldn't be anything in here. So you can say that charge inside this is supposed to be 0. Nothing. Oh, I don't know. Just like no charge. Let me say no charge. No charge. Does that make sense? Give you some sort of like a common sense is being built here, I hope. Yeah. So when you say, hey, there's no flux left inside this closed surface. So that means inside this closed surface shouldn't have anything, because if there is some charge inside, you should have like evidence, like a crime scene or something. Like you should be able to investigate and okay, you left some clue here that there is the leaking out of the electric field from the closed surface. So there must be some charge inside. But when you look at this one, I don't have any evidence showing that there is any sign of piercing out electric field or piercing in electric field. So I can conclude that there must be no net charge inside this closed surface. Does that make sense? All right. So if this is good, I think I'm going to end today's lecture at this point, because I think it's sort of like it's like a theory or some sort of like there's so many components that built into this. And I think I want you to think about this a little bit, or sort of like have this thing running in your head for a while. And then I think we can have like a better time to develop this one after the exam. Sounds like a good plan? All right. And for those of you that really want to jump ahead and see what's next, you can try calculating this one, and then we can go through these problems together next time. Sounds like a good plan here? All right, guys. So if this is good, I think I'm going to cut this one short a little bit, and we'll continue on after your second exam this Saturday. Okay. All right. If there's no objections here, all right, guys, take care, and I'll see you guys next time. Okay. But anyway, see you this Saturday first.